Thanks. So I guess it wouldn't be a proper 2016 technology conference without somebody talking about Docker. So I'm going to take care of that today. What I'm talking about in particular is running GPU encoding from a container. So a little bit about me and why I'm talking about this. Started off out in San Francisco after Matt and I's just atrocious job before that. Was working with encoder transcoding, particularly live transcoding. So this is like running FFmpeg and friends in the cloud. Moved on after that down to LA to Otoy, where I did a lot of graphics rendering on GPU. So this was like, all right, I did FFmpeg rendering, now I'm doing GPU rendering.
And move the mic to your t-shirt.
Okay.
Which one is this one?
Fix me up.
Is that better?
Is that better?
Yeah.
Sweet.
Okay.
Okay. So running GPU stuff in the cloud, a lot of CUDA stuff. And now this year went over to Mux, co-founded that in January, where we are Dockering all the things. So experience with FFmpeg, then GPU rendering, and now all the Docker. So I wanted to do an experiment to see what does it take to put all these things together. Mostly I was curious around these tech circles that specifically the video meetup, we talk a lot about video codecs and browser support and even hardware decoding, but no one ever really mentions the hardware encoding software that's out there. So we're going to talk about hardware encoding in the cloud in a container. So part one of this is the encoding hardware. Is it why would we even consider hardware? X264 is great. A lot of research is going into doing that. The new VP9 encoders and stuff like that. But when you have some dedicated hardware, you can get really big boosts in speed, maybe at the cost of quality. We'll talk about a little bit later. Power, cost savings. I'm not going to answer those questions, whether or not it's worth it. It's highly dependent on the content that you're streaming and what your use case is. But we'll talk a little bit about that. Most importantly, the hardware is out there. There's Nvidia and Intel are constantly producing this better and better versions of this hardware. The downside of all of this is it makes it much more complex to run. So GPU encoding might not be exactly what you think. Say GPU encoding because a lot of times that's the way you hear it pronounced. You hear you need a GPU hardware to do this encoding, but most often you're not actually doing the encoding in the GPU part of the chip. They just happen to have these ASICs built in. So there's multiple components that you might possibly do encoding in. CPU is our traditional X264 encoding. GPU encoding so Nvidia has their CUDA drivers. There's also OpenCL that can run on most any GPU. This would be rendering on the GPU cores themselves versus the ASIC, which is the application-specific integrated circuit. So all of these GPU vendors have these chips built on have these separate chips actually built onto the hardware themselves. The CPU can kind of handle all of the tasks. The GPU can handle most of them except for entropy encoding. And then the ASICs is they're built specifically for one function and with varying support between the pieces. Implementations here, NVIDIA, you can run things with CUDA or NVENC. That is their dedicated chip. Intel has their QuickSync chip. AMD has their VCE chip, as well as their GPU side implementation, which is OpenCL. I've got main concepts written over here on the right because they actually produce some GPU only rendering or encoding software that runs on either CUDA or OpenCL, but then offloads the entropy encoding to the CPU. So this is what you really want is kind of a hybrid approach where you can do fun things like color space conversion, scaling, and filters on the GPU side of things, but the CPU is still going to need to do that entropy encoding. Works better with prediction and look ahead. It's also a lot nicer if you're not doing live things, so you can work in chunks split across multiple CPUs. So the CPU and specialized hardware kind of take the same role. The specialized hardware can obviously do a lot of the same stuff that the GPU can do if it's there. Okay, so taking a step back for a second, this is really the meat of the talk. Let's talk about containers. In particular, we're talking about Docker, obviously. The they're not virtual machines. Like, you've probably seen this before. Like, I don't know why there's this misconception. Actually, I do know why there's this misconception, I think. That the Docker is basically just like a slimmed down, glorified virtual machine. And that couldn't be further from the truth. And this is like a misconception I want to clear out like from the get-go here. Even on Docker's homepage, they have this comparison of containers to virtual machines. It's like, why is that the initial comparison? I'm like, blame Vagrant here. Because like 3 or 4 years ago before Docker, we were like, oh, wow, it's really hard to build our applications and run them consistently. So Vagrant came along, it's like, oh, let's build a nice little VM here, we can run our things. Then Docker came along and kind of did the same thing from the development perspective. So maybe that's where some of the the misconceptions come from. Also, like the Docker file does start with something like from Ubuntu or something like that, which doesn't help. But a container at the end of the day is really just a process. And if you don't take anything else away from what I'm saying right now, it's like invert your thinking about a container from being like it's kind of like a VM to like it's a process that's got restrictions on it. And those are optional restrictions. So here on the left, run a Docker container with a simple sleep command. Just sleep forever. On the host machine on the right, the same machine, but this is on the host, not inside a Docker container. If you run a PS and look at the processes running, you actually see number 2970 there. Is that sleep running? Like this is, if this was in a virtual machine, you wouldn't see that at all. So let's take it a little step further. On the left, same sleep command. On the right, we're going to run a Docker container and get a shell into it. This time we've given it one extra bit of power, and it's in the PID, it's a host PID namespace. So now we're inside the container on the right, and we list the processes. We see the process from the other container. That's kind of unusual, I think. Probably not what you would expect. And then we can just kill it. So we just killed another container from inside one container. So it's super powerful, the amount of permissions you can give to a container. So the reason I'm showing you this is when we talk about GPU encoding and talking to hardware, we may or may not need to give it certain permissions. At the end of the day, you can give a Docker, you can basically turn a Docker run command into a shell script. If something works on a host, it should just should work in a container. There's really no excuse to like say, oh well, this is too complicated to run in the container. If where there's a will, there's a way here. You can strip away components that make Docker what it is until it basically becomes the host. And most complications I've found in practice of running Docker come from actually managing volumes. So not the running and the restrictions and stuff like that. Okay, so why would we even bother with Docker here when talking about hardware encoding? Well, it's the same as any other reason you'd want to choose Docker. Consistent builds, when you're running multiple versions in the cloud, like, man, we had some, I remember trying to run multiple FFmpeg versions in the cloud with like dependency issues, and basically you have to pick a new machine for each one. Docker solves all of this really nicely. I mean, how many man hours in this room have been spent trying to get like a certain version of FFmpeg to build with a certain dependency? Like Docker can solve all these problems. And if for no other reason, especially with hardware libraries can be invasive. What do I mean by that? Well, this is from the FFmpeg docs. If you try to install the Intel Media Server Studio, it might just overwrite your system libraries and break the system. So it's like, it might be nice if we could package this stuff up into a Docker container. Okay, so back on to what the actual hardware encoding stack looks like. You've got your hardware at the bottom, the actual GPUs. You've got your host OS, your drivers, Docker running, and then in the containers, you can run all of the libraries involved that you need to run on that hardware. The tricky part here, this is where all of the difficulty comes from trying to run on hardware, run hardware encoding from a Docker container, is the actual driver. So the driver in all of these systems has two parts. One is the actual kernel module, and in some cases that involves kernel modifications as well, and the user space driver. And these have to match exactly. If they don't match, then it's just not going to work. So that basically means I've deployed a host out there with a certain driver version, and I need to have that same, the sibling driver, user space driver, installed in the Docker container to get it to run. So step one of this, building the container, you build it just like anything else. Nothing special here, except you can skip that kernel module step. You don't need it here. And also, like, it's nice to try at this stage to keep your container small. This is just like Docker in general, just so it doesn't take forever to transfer them around. A really nice tool that I found here is the Nvidia CUDA Docker repos. Nvidia has done a lot of really nice work, and we'll see more of it in a minute around running the stuff from Docker. And so it's a nice starting point that has all of that, the CUDA libraries and stuff ready for you. So you've got the container built. We need to build our prepare the host. Obviously, you need Docker installed. You need to install your kernel drivers. And in some cases, that also involves running kernel patches in the Intel world, at least. So a few ways you might deploy this is building the machine image. You might use your favorite provisioning software like Ansible or Chef or those things. One place where I had some fun here was getting fancy with Docker. We were talking earlier about the permissions that you can give a Docker host or a Docker container. One in particular is the sysmodule capability, where the container can't do anything else on the system outside, like it can't break out of its shell except for writing kernel modules. So loading and unloading kernel modules, this is like fun, but it's probably not a good idea in practice. And also, you'll need to create your device nodes. This means like /dev/NVIDIA and /dev/NVIDIA UVM in order to load them into the container. This can be done at boot time with like a script that runs to load them up or other methods, but that can be a real complication when you want to like restart machines in the cloud. So some helpful tips for installing those drivers: get rid of all the Nuevo stuff immediately. It's going to cause you problems. The run files from NVIDIA have a lot of options for picking out the individual pieces that you want to use. Also, there's graphics driver PPAs, repos available on Ubuntu that work pretty well on most versions. You can also install all of the normal CUDA stuff on your host because you're not going to need it, you're not going to use it, but usually it's bundled with the install scripts for the kernel drivers. One really awesome project that I found was this CoreOS NVIDIA project from Clarify. We can thank our like artificial intelligence friends for like help like really making all of this stuff mainstream. But this is a really nice project where you can drop in your NVIDIA version, your CoreOS version, and it'll just kind of build those kernel modules for you and make it really easy to load them onto CoreOS. Intel, this is where this is like biggest disappointment about my experiment here was trying to run Intel stuff. I was naive in thinking that somewhere out there I would be able to get a cloud NVIDIA chip that had one of their GPUs available to me. And as far as I can tell, that's not the case. I was expecting like one of the bare metal providers to have one available. If anybody knows, I'd love to hear about it, but I didn't have one available. I was able to do all of the same container level stuff with the Intel libraries and build the container, but as far as the actual kernel module, yeah, maybe next time. Okay, so let's talk about actually running this. So the old-fashioned way of doing this is doing this with a normal Docker command. Docker run, set your devices. This is why you need to load the device nodes ahead of time. There's no way to do this and pass these in if they don't exist. And this just works. The pros of this is it works with the existing orchestration tools, and there's nothing else to install. The cons is this requires the driver version to match exactly. Like the application, or the user space driver and the kernel driver versions need to match exactly. And obviously, you've got to manually load the device nodes. But thanks to NVIDIA, there's now a much better, newer way. NVIDIA has released this project, NVIDIA Docker, basically CLI wrapper for running Docker commands like this. And this takes away all of those requirements to preload the device nodes, as well as building the user space driver into your container. So this also installs as a Docker plugin, which is really nice for like working with other orchestration tools. But the biggest win here is there's no longer the need for the user space driver in your container. This works by, it's a really lightweight wrapper around Docker. That when you run this command, it mounts a volume containing that user space module, user space driver into your container, and also initializes all the device nodes. This already has support in Mesos. Kubernetes is like, it's in the works. I think it's already in a PR. In Swarm, there's some talk around it. On the Mesos side of things, like the reason I say this is super lightweight, like Mesos didn't integrate this, they just built it themselves. So this is a really nice tooling, like this is the way forward. A lot of projects that were doing it the old-fashioned way are now deprecated. Okay, so we've got all the pieces built, we've got our host running. Let's talk about actually doing the encoding. So I built a Docker container, push it up on Docker Hub that has the Nvidia libraries built for the NVENC, NV resize, which I'll get into a little more detail in a minute, X264, and FFmpeg. So starting with a video, let's get our favorite high complexity test video and run a command like this. So Nvidia Docker run, pass in the volume that has the video in it, do some settings here. Can I see? So notice this is interesting. Two pass true. This is an NVENC setting, and as it might lead you to believe that this is like real two-pass encoding. It's not that at all. This thing tripped me up when I saw it, but really what they've done here is it's two-pass on each frame. So there's like an extra estimation step that happens on each frame of the encoding. This helps it still be super fast, but it's not anywhere near as good as the actual true two-pass encoding, as we'll see in a second. So some results from running this stuff. On the left, I have time in seconds for the run of the single cloud run encode at 6 megabits. X264, about 15 seconds. This is on a fast preset because I felt like that was kind of fair to compare to the GPU encoding. So the K520 GPU is the older Amazon instance. That's the G2 instances. The K80 is the new fancy P2 instances that just came out or were released a couple weeks ago. And then finally, there's a GTX 1070. So I was really interested to see the runtimes of the K80 go up. This is the newest hardware. This is Amazon. They just released this. The other ones have been out there for 2 years. So what's really going on here? What's really going on is that these are still both the same NVIDIA architecture. They're both Kepler-based. I guess that's what the K stands for here, I assume. So there's Kepler, Maxwell, and the newest is Pascal. The GTX 1070 is Pascal. They're brand new this year. And you can see that their hardware encoding chips have significantly increased over the past couple of generations. Also, I ran the VMAF scores across these. I wouldn't read too much into this. Because I really didn't go deep into tweaking these encoding settings, to be fair. I just wanted to get some ballpark numbers. But you see X264 is, as we might predict, better. And then the rest of them are about the same, maybe with the newer architecture a little bit, with a slight improvement. But I think these are all, as you'll see in the next slide, just kind of just because of the way the numbers came out. They're super close. So I ran a VMAF chart per frame on this stuff. You see all the GPU results are pretty overlapping and pretty much the same, with an interesting result from the X264. I pulled that up with size per frame aside. Is just that the X264 seems to have gotten a little greedy at the beginning there. Like I said, this is still one-pass encoding, so obviously two-pass encoding would have been much better. The more interesting stuff with this GPU encoding comes when you're talking about doing multiple things on one GPU at once. And this is where they really excel. So one-to-N encoding in this case, we might take the X264 input, do a CPU decode, and NV resize. So the NV resize is NVIDIA's implementation of GPU scaling that does a zero memory copy into the NVENC encoder. So you can run all of this on one GPU. And this would be analogous to what you would do in multi-bit rate encoding. So similar command here. We've added this complex filter to FFmpeg, which is the NV resize command. Map that out to all of our NVENC output nodes. So in this case, I'm doing 5 at stepping down bit rates. So the results here, I ran it first with X264, still using the NV resize. I'm not really sure what's going on under the hood there, but it's pretty slow. Or standard, I guess I would say, compared to the others. The 520, again, performs better than the K80. Again, the 520 is that older G2 instance. And then the GTX 1070, the new Pascal architecture, just blows them all out of the water. It was really impressive how fast this was. So that last metric is actually a bit of a lie, though. the GTX 1070 is a consumer card that I have on my home machine, and Nvidia has a restriction that you can only run 2 simultaneous encodes on a GPU. So that's actually doing them sequentially. So that's doing 2, then 1 to get the total 5, but it's still ridiculously fast. So then I ran just to see what would happen if we went ahead and ran this multiple times on the K520, the 2 types of Amazon instances. This is just running the same 1 to 5 encoding twice at the same time. So 10 total encodes, and the speed doubles, or the time taken doubles exactly, which just kind of shows that the encoder chips are maxed out. Okay, so finishing up here, what's really interesting about this is that the hardware producers are really putting in a lot of work here. The latest generation of hardware, the Nvidia Pascal chips and the upcoming Kaby Lake stuff from Intel, is like really impressive speed-wise. They've also got great support, so HEVC main 10-bit encoding. The Pascal chips are 2 times the speed at 4K over the previous version, which was Maxwell, which is a version ahead of what the Amazon chips are. And then also doing HEVC at 8K. Intel Kaby Lake, I think similar things here, 4 times real-time encoding at 4K at 30 frames a second, which is pretty awesome for a single chip. And then the biggest, most exciting thing I think here is the VP9 encoding on the new Kaby Lake chips. So the future of this, new hardware in the cloud would be super interesting to run some more benchmarks on. The SoftLayer and Azure both have the Tesla M60s, which are at least upcoming on their clouds, which the M stands for Maxwell, I suppose, and which is the generation 1 before, which should be significantly better than the AWS generation. It'd be really cool to see something along the lines of the Intel Docker runner, or maybe just have this stuff built natively into Docker for mounting user space drivers. GPU constraints are not a thing, and I don't know, like in Docker containers, a lot of the power comes from limiting memory and CPU. Right now with this approach, you can't do any of that kind of stuff on GPUs. I'm not even sure if that's possible. Also, I can see a lot more workflows with like computer vision and machine learning, like not just encoding, but if you're running these kind of things on streaming videos, then running them in a Docker container is a great way to go for all of the previously mentioned reasons. And finally, like a Docker video encoding ecosystem where you can do all of this stuff in Docker is super powerful, as well as like from a community standpoint, if all of the tools that we're all producing all of the time, like I don't know how frustrated and how many times I've spent like trying to get this silly little binary to build on my machine, just wasted tons of time. Like if you're building these kind of tools, take the 2 minutes to build a Docker file. If you get nothing else out of this, like a call to action here, build a Docker file or include a Docker file in your binary open source stuff. So yeah, that's kind of where I ended up, and thanks. Any questions? Where's lunch?
Right. Sweet. Oh no. I was expecting the lunch to be that. Yeah. Oh no, I'm looking at Colleen. No. No ASCII dicks on the website this year, Colleen. Left my computer unlocked for 5 minutes. Colleen pushes an ASCII dick to our website. Okay, she didn't push it. I didn't check. I pushed the code. Didn't check the footer. Okay, so I don't think lunch is quite here yet, so feel free to roam around. Quick mushy story about Adam real quick. I was talking about like working together in Athens. We come out to San Francisco. He works on multiple transcoding solutions. I think like, I don't know, becomes one of the best people I know at transcoding video. And we start a new company. We're like, hey, you're probably the best person at building transcoding products. How about you build an analytics platform? And so there we go. New company, woo! So anyway, if you have any questions for Matt or David one-on-one, I think a few like people raise their hands towards the end of the last one. Feel free to grab them now while we wait for the lunch to show up. There's drinks over here. Lunch will be back on this platform. Otherwise, we'll see you again after lunch. Also, if you haven't submitted lightning talks yet, do so. Flavio, I'm looking at you. Hadar, I don't know where you are, but I'm looking at you too. Okay.